before we move on from graphs of sinusoids and start talking about the graphs of tangent and cotangent, let's take a look at this problem here. So we're given this data, which is from something to do with the Navy, and what's given is the fraction of the moon illuminated each night for every night in January 2015 as well as November 2015. So for example, on January 1st, 2015, 84% of the moon was illuminated. So 16% of it was dark. On January 5th, it was a full moon. On the 20th, 21st, and 22nd, most of the moon you couldn't see. Okay, so we have this data for January and November 2015. So the first thing we want to do is let's put this data into Excel and plot it on a scatter plot. Okay, so here's all the data here, and here's a scatter plot of that data with the day of the month on the horizontal axis and the fraction of the moon illuminated on the vertical axis. All right, now note that this is real data, okay? This comes from some research with the Navy. All right, so what do you notice about this? Well, it's clearly sinusoidal. It's closely following a sinusoidal pattern. And this gets back to a point that I've been making as we've talked about the graphs of sinusoids, is that the sinusoids are the heart of all periodic functions. If you think about anything in nature that is just naturally periodic, and the fraction of the moon illuminated day by day over the course of a month is as naturally periodic as you can get. So anything that's just completely random is I guess the way I would describe it. Like a completely random periodic variation is going to be sinusoidal. So a good example of that is the average daily temperature, right? We looked at another example like that, the average daily temperature in Anchorage, Alaska over the course of the year. So it's naturally varying, right? Because you go through the seasons, so it's going to get hotter and colder and hotter and colder. But that's as random as it gets, right? As far as that variation. The periodicity is completely random. It's like purely natural. Okay, well in that case, that's why when you put that variation on a plot, it's going to be sinusoidal or very close to sinusoidal. And so that's just something to keep in mind of how the sinusoids are the king of the periodic function. And this point is more even strongly illustrated when you get to Fourier transforms. When you can see that the sinusoids, you can use sinusoids to create a sum of sinusoids to create any periodic function, like even a square wave. You could decompose any periodic function, a triangle wave, square wave, whatever, into like a sum of sinusoids. Okay, so now the next thing we want to do is I'm going to put each of these data points for each of these months into a regression calculator. We're not going to do the regression here. We get into regression in detail in algebra and statistics, but I'm going to put each of these data points into a regression calculator. Let's see what we get. Okay, so here's January and here's November 2015. And you can see, so, the data points aren't 100% purely sinusoidal because the correlation coefficients aren't exactly 1, but the correlation is still very good. And the resulting equation for this sinusoid is shown here, and for this sinusoid is shown here. Okay, and so now what we can do is let's rearrange each of these equations to see how the curve is transformed. So we've got sine of, let's factor out a 0.2027. So x plus, and then 0.6274 3.095 plus 0.5 0.5419. Okay, so we've got a vertical shift of 0.5419, a horizontal shift to the left of 3.095, scaling about the x-axis by a factor of 1 over this, and then scaling about the y-axis by this factor. So what's the period? It's going to be 2 pi divided by 1 over this. So 1 over 0.2027. That's what we've scaled up about the x-axis. We've stretched about the x-axis by this factor. So 2 pi times this, about 31, and that makes sense. That's the period here, right? It's 1 month. So P is 31, approximately 31 days, right? Because the units of period are the horizontal axis units. You specify the period of a sinusoid based on the horizontal axis units. Every 31 days, this repeats. Okay, now the horizontal shifting about 3.1, that's days to the left. What's going on there? Well, if it wasn't shifted, this would like start here. Well, so in order to make the curve match up, it needs to shift it a little bit, right? And the shift it needs is about 3.1 days to get it to line up. Okay, now 0.5419 of a vertical shift, that's 0.5419 fraction of the moon illuminated. Well, okay, we can start with, let's start with the scaling about the y-axis. If you look at this data, you can see that the amplitude of this variation is about 0.5. So you need to scale from the about the y-axis about 0.5, because you're going to multiply you're going to go from an amplitude of 1 to 0.5. Now the vertical shift of 0.5419, the fraction of the moon illuminated, is because the variation it's not oscillating about 0, it's oscillating about 0.55, like right in this region here. So you want to shift it to what it's oscillating about, like kind of like what the average fraction of the moon illuminated is. The average of all the data, that's kind of the midpoint. And so you want to shift it up to where it oscillates about that midpoint. So that's what this is about. Okay, and again, this factor here was to stretch the period from 2 pi to the period that worked for the data, about 31, from 2 pi to about 31. Okay, if we look here, so we've got, let's factor out. So 2.3, 11.33. Okay, 0.2094, if we take the reciprocal of that, so we scaled up about the x-axis by this factor, so let's multiply that times 2 pi 30. So yeah, because November only has 30 days. P is approximately 30 days, right? So again, this factor was applied to stretch out the normal frequency of the sine curve, 2 pi to about 30. Now we have a horizontal translation of 11.33 days. And let's see, so that's maybe about here. So we're starting with sine. And so let's see, something like, if you started out here, then you would start down here, and I guess that's not, I'm trying to make it. And yeah, you just need to shift it. So it would be about 22. You're going to be shifting it to where when you shift this 11 over, about 11 over, it's going to end up being to where this comes here. And it's just to follow the data. It's where the phase is about where you can see the data is starting, not at the standard start point of the sine curve, right? It's not starting like this, or it's not starting like a pure cosine. It's starting like in the middle. So you need to shift it to where it starts where it's supposed to start. And that's what this does. The 0.4962, again, that's like the kind of the average. You could think about the average here is where it's oscillating about, the average of the data. And the amplitude looks like to be about 0.4. And so, yeah, you scale the amplitude of 1 down to where the amplitude accommodates the data, and then there's the amplitude, and then you shift it up to what the average value of the data is, which is what the curve is going to be oscillating about, which is around going to be 0.47-ish. Okay, so that's it for the graphs of the sinusoids. Let's move on to the graphs of tangent and cotangent.